All right, so let's talk about the ruler postulate. Now, in geometry, a rule that is accepted without a proof is called a postulate or an axiom. Sometimes we don't need a proof because it's just a definition, such as when we say that parallel lines never touch. That is part of the very definition of what we mean by parallel. So proving that parallel lines never touch doesn't make much sense because that's the very definition of it. Other times a postulate or an axiom might be one because we might not prove it because it's so obvious that it's difficult to prove it. There's nothing to prove, it's just obvious. One of these is called the ruler postulate. Now the language here might seem confusing, but I'll try to break it down. Now rather than using x1 and x2 for right now, I'm just going to break this down and say on this line, we're going to say we can put numbers on this line at certain intervals. So let's say here at where A is, that is a 5, and then over where B is, and perhaps we add like several lines here, that B is at 10. Okay, so how do we know what the distance between A and B is? Well, we do something simple. We do 10 minus 5, and that tells us they are 5 apart. Okay, what I just used is the ruler postulate. Okay, the ruler postulate, as we now go through the more official language, says that the points on a line can be matched 1-to-1 with the real numbers, meaning that these dots that we have on a line, we can apply a number to them. The real number that corresponds with a point is the coordinate of the point. Okay, so we're getting some definitions there. So whatever number corresponds to A and whatever number corresponds to B, that's the coordinate. The distance between those 2 points, A and B, written as AB, so that's another definition. Here's how we write the distance between A and B, is the absolute value of the difference of the coordinates. Now when they say difference, we're talking about subtraction. So we subtract the 2 coordinates, in this case x2 and x1, we subtract them, and that tells us the answer. One little addition is the absolute value symbols. They are there to make sure that the answer is always positive. If, for example, in the previous one I had done 5 minus 10, then I would have gotten -5. But that doesn't make any sense when we're talking about distances. I can't go outside and run -5 miles. So we put the absolute value there to acknowledge that all distances are going to be a positive. All right, so here's our problem. We want to measure the length of S to T. Well, S was at 2. Looks like T was at 0.4. So the distance of S to T must be equal to the absolute value of the difference of the coordinates. And that's what I just wrote. So that's going to give me an absolute value of 3.4, which is just 3.4. We also could have written it as 2 minus 5.4, and that would have made this a -3.4, but when we do the absolute value of -3.4, we get the same thing. So either way, it comes out the same. All right, now let's talk about congruent segments. 2 segments are congruent if they have the same length. You can say that the length of AB is equal to the length of CD. Notice we're talking about the lengths there when we use the word equals. Or you can say that AB is congruent to CD. Now, and actually I should say, because there's that line above there, that the line AB is congruent to the line CD. This symbol that looks like an equals with a squiggle above it means congruent to. Now this right here is kind of showing a bit of math grammar. Now notice right over here where we just got AB, no line above it. This is to say the length of AB is equal to the length of CD. So this is the way we're going to write when we're talking about lengths. When we put the little line above it, we're actually talking about the shape instead. So in this case, we're talking about the line itself and not the length of the line. Lines are congruent. Lengths are equal. Okay? All right, so if we want to compare two lines to see if they are congruent, we're going to plot J, K, L, and M onto the coordinate plane. Then we're going to determine whether or not those two are congruent. So first, to plot J and K, so J is at -3, 4, label it with a J. Then K is at 2, 4, label it with a K. There's the line JK. Next, L and M. L was at 1, 3. M was at 1, -2. Draw the line. Now we can actually, in order to find the lengths of these, we can use our ruler postulate still. We've got a line in which the dots correspond with a specific number. So JK is going to be equal to the absolute value of the difference of those coordinate points, which is going to be 5. Now I know some of you are saying, I counted the squares and that's easier. You're absolutely right, student. Way to go. That's fine. Right now we're just trying to emphasize what the ruler postulate is. And sure, counting the squares works just fine. But also think about what would you do if the graph didn't have squares to count or other things that could make this easy. What if those helps are taken away and all you know are the coordinates? Well, now this helps a little bit. All right, so next, LM. We've got numbers that correspond with LM as well. So I could do the absolute value of -2 minus 3, which is then going to give me -5, which is equal to 5. Well, they both equaled the same, so that tells me two things. The length of JK is equal to the length of LM, and the line JK is congruent to the line LM. All right, let's do another postulate. This is called the segment addition postulate. This only works with collinear points. Collinear mean they all exist on the same line. A, B, and C are collinear, with B being between A and B. And D, E, and F are not collinear. E is not in between them. It is not on the same line. Now, if you have 3 dots that are all collinear, one of them must be in the middle. And that is important for the language that this is about to use. So it says the segment addition postulate. And in fact, to really express how easy this can be, I'm going to first express it without the use of all that math language, and then we'll go through what the math language is saying. So let's say that A to B here is of length 5, and B to C is of length 1. So what is the length to go from A all the way to C? If you said 6, you're right, and you know how to add. Yeah, that's absolutely right. All we're doing in the segment addition postulate is adding these two segments to get the whole. B, the dot in the middle, cuts it into 2 different segments. And if I know what both of those are equal to, I can add them together to get the entire one. And that's what segment addition postulate is saying. If B is between A and C, there's B cutting it into 2 different segments, then A to B plus B to C should be equal to the A to C. Okay, that's all it's saying. All right, so here we're trying to find D to F. Notice we got E in the middle. Segment addition postulate would say then that D to E plus the E to F should tell me what D to F is equal to. Well, we've got 23 plus 35, which is going to be equal to D to F. So D to F equals 58. Similar problem here, although notice this time they do tell us how long the entire one is, and we're trying to find a smaller segment. But the theorem, the postulate, still exists. So F to G, one of the smaller segments, plus G to H, the other small segment, should be equal to the entire segment. Now we know the entire segment was 36. We know F to G was a 21. So if we subtract the 21, if we take out that entire length, all we're left with is G to H. And so G to H should be equal to a 24. All right, we're going to do it one more time. Now we've got this map here. It shows 3 cities that are about on a straight line, with Tulsa in between, cutting it into 2 segments. So our first segment, Lubbock to Tulsa, if we add it to the other segment, Tulsa to St. Louis, that should tell us how long it is to go from Lubbock to St. Louis. Well, Lubbock to Tulsa is 377 miles. Plus, we do not know how long it is from Tulsa to St. Louis, but we do know that to go all the way from Lubbock to St. Louis is 738 miles. So once again, if we just take out that distance of Lubbock to Tulsa, then what we should be left with after we remove that distance should be the remaining distance of Tulsa to St. Louis. So that, I'm just going to quickly type this in, 738 minus 377 is 361. All right, good luck on the homework.